Welcome to wave-particle duality. Arthur Compton was an American physicist, and he noticed that if a wave is incident upon an electron inside a material at rest, then that electron can be given enough energy to escape the material. And the wave had also been affected by this interaction. The wavelength lengthened. So the velocity of the electron went up and the wavelength went up. This represents an energy increase to the electron and an energy decrease for the wave. He called the change in wavelength the Compton shift. And he concluded that light waves have particle-like momentum, because here we have a wave incident upon a particle, the wave loses energy, the particle gains energy. It's the same effect that you would have in a collision. This effect is called Compton scattering. And he did this work in 1923. In 1927, he won the Nobel Prize for it. In 1924, Louis de Broglie, a French physicist, did some work that went further than this. His idea was that all particles have wave-like properties. He took Einstein's equation, E equals mc squared, and he combined it with the equation for the energy of a wave. And if you rearrange it, remember that the wave equation can be substituted in here. And you can link the wavelength of a wave to the mass of the particle. Here we have a mass, here we have a velocity, and you'll notice that that is a momentum. So de Broglie's final equation was that the wavelength of any particle is equal to the Planck's constant divided by its momentum. So if we have a particle with momentum, then it has a de Broglie wavelength. And that means that particles behave like waves and they can be diffracted, so long as you have the right sized gap for them to pass through. Remember, you get maximum diffraction when the size of the gap is approximately equal to the wavelength of the wave. Here we have an electron diffraction tube. So we have a voltage supply and we have a heated element releasing electrons through the process of thermionic emission. We have a positive anode to accelerate the electrons through this gap. And here we have a target, and that target is usually made out of graphite. And graphite occurs in sheets with a lattice structure on each sheet. And this regular lattice structure has holes in it through which the electrons can diffract. So they pass through the gap, they hit the target, and they diffract. And because there are lots of little holes next to each other, they will diffract and overlap, and you will have an interference pattern on the screen. Let's look at a simulation. In this simulation, we have some controls on the left-hand side, and we have an image on the right-hand side. And this is the image that would be seen on the fluorescent screen. When the electrons strike the screen, they create a glowing effect, and that's what we are seeing. We see a central point and then two circular rings, and that is the diffraction pattern of electrons. We can change the controls and see what happens to the pattern, and you can even take measurements of the rings. If we were to increase the acceleration voltage, then we can see that the gap between the rings reduces. And if we reduce the acceleration voltage, if the electrons are traveling more slowly, then the ring spacing increases. And if we look at the wavelength of the electrons, the de Broglie wavelength, we can see that when they are moving faster, that wavelength decreases. And if we reduce the velocity of the electrons, the wavelength increases. So we just saw that as we increase the voltage accelerating the electrons, the wavelength of the electrons decreases. Let's look and see why that is. So we know that the electrons are being accelerated because work is being done on them, and that work is equal to the charge multiplied by the voltage. And all of that energy is becoming kinetic energy. And therefore, the charge on the electron and the energy that that gains is going to be equal to half mv squared. We can rearrange for velocity, and we get this. And we recall that momentum is the mass times by the velocity. We can substitute this in here, and we end up with and in de Broglie's equation, so the larger the accelerating voltage is, the smaller the wavelength will be. Being able to calculate the wavelength from the acceleration voltage helps with the analysis of these diffraction patterns. The closer the wavelength is to the size of the gaps in the lattice, the greater the diffraction. And you can take measurements on the fluorescent screen and analyze this data to make calculations about the size of the gaps in these lattices. This gave scientists a new technique to analyze materials. A very famous application of this type of analysis was used in the discovery of the structure of DNA.